Hello, does this work?
Hello.
Hi.
Hi, I think it works.
Great. Do you guys want to go ahead and show me your faces so I'm not talking into the void? Thank you. There's still people entering, so I'll start in a few minutes. How's the microphone? On?
Fine. Yeah, it sounds fine to me.
Thank you.
Bonjour.
Hello? Well, I'm very sorry about all of the technical difficulties with the Zoom information, etc. Okay, I think things have calmed down. I'm going to try sharing my lecture. All right, can you all see this?
Yes, we do.
Yeah, it works.
Okay, great. Sorry, I am just in all the, trying to make sure I can see the chat and the participants as well, so I can see if you guys have questions that you want to write out. Okay, all right. I think this is set up now. Let's see. Okay, hi, welcome to Mod 101. I'm Alex Kekagaich. As you can tell, this is an online course. So I'm really gonna try to do everything possible to make sure that this can be an engaging and an interactive course for you. First of all, I want to give you like a good structure of what I'm going to be discussing at each lecture so that I'm not just like talking for 2 hours, and I know it's hard to focus on Zoom from personal experience. So first, I'm going to just give you a brief introduction to Zoom etiquette for this class, and then I'm going to go into a motivation for one model, and then a bit of an overview for the course, some practical information, and finally, I'll get to the meat of the lecture on cognitive modeling. Oops. Okay. So, I mean, I guess you guys are pretty familiar with Zoom already, but I would just ask that if you can have your videos on, to have it on, because it helps me to see if people are confused. It's, I think, a lot nicer for everyone if we can all see each other, feel a little bit more like a community. If you have questions for a class of this size, please use the raise hand function so that I can see. And you can also, if you want to ask a question, but you'd rather type it out, you can write it into the group chat. If I'm not responding to any questions and it seems like I'm not noticing them, feel free to just unmute yourself and say, hey, you're not paying attention to these questions, or something like that. Okay, and then there are a couple of things that I added in the settings to try to make this more interactive. So one of them is I added, if you can, actually I don't know where this is. For me, it's under the link participants, but there's something called nonverbal feedback. Do you see that? So basically you can write yes, no, go slower, go faster, request a coffee break. Do you see this?
Yes.
Yeah. Okay, so let's do an experiment because I've never actually used this before.
I totally did not see those. Where are they supposed to be?
Thank you for asking. Where are they supposed to be? For me, it's under the participants. So if you click on participants, it's at the very bottom, but that might be different because I'm host.
Oh, yeah. Okay, I see it now.
All right, so if you see it, then click on yes.
Yes.
Let's see. All right. Somebody clicked a thumbs up, which is not following the directions, but I'll accept it. Okay, great. It's quite funny. Okay, it seems like most of you. So I'm going to, I'm going to go ahead because I think you can also just Google how to find it maybe later. Somebody has their microphone on, so I'm going to mute all of you who have your microphones on. Sorry. Please just remember to mute yourself unless you're actually asking a question, because otherwise we'll hear your very embarrassing background noises and you'll be so embarrassed because it's recorded. Okay, so I think I can clear all of these. So you can also, if I'm not making sense, you can request to go slower. As you can see, if you go to more, then you can request a coffee break because this is a 2-hour class. And if there's a lot of people who are requesting a break, then I will give you a 5-minute break. Okay, that is one of the 2 options. The other option, if I can figure out how to use it, is to, oh, here, yeah, to have polls. So I'm gonna do a little introduction poll now. Here, launch poll. So you should be seeing this come up. Do you guys see it? It's just basically a poll on your background. What is your major? How do you, kind of like mathematical training do you have? Great, I can see the results coming in. Those of you who came in late, we have a poll going on to kind of test the interactive features. Okay, so this is the majority of you. So I'm going to end the poll now and share the results. Wow, this is really cool. Can you see this?
Yeah.
Yeah, okay, so what is your major? It's pretty even among the, I mean, slight increase for modeling over other ones, but pretty good. So we have a very broad range of majors. How comfortable do you feel with math? Thankfully, no one's mind goes blank when they see an equation. That's good to know for this course. And kind of a range of some people advanced, some people less advanced. That's okay. Okay, great. This is really cool. Okay. So that's the introduction to Zoom. And hopefully that helps you feel more interactive, as if this is a in-person class that you can interrupt. Okay. Great. So let's talk a little bit about some of the motivation for modeling. So before we talk about why we should model, let's first talk about what is a model. This is a picture of Le Corbusier, famous French architect, with a model of the Villa Savoye. This is obviously not the actual building. This is the actual building. And this is a picture of him with a model. So what is the point of Le Corbusier making a model of this building? Anyone want to venture a guess? No takers. Anyone want to, any possibilities at all? What is the point of an architectural model? Yes, Elizabeth. Elizabeth Fleck, did you raise your hand?
Sorry, I was still muted. There's like 2 mutations on my computer. So to have a visualization and to see the proportions of the building, to make it more intuitive to, I don't know, imagine how it's going to look later.
Yeah, that's a good answer. Anyone, any other answers?
To confront a theory with the actual possible implementation, I mean, with reality.
To confront the theory with the reality, yeah, that's another, what do you mean by confront exactly?
When theorizing, you never know if it can actually be implemented or if your idea can actually exist.
Yeah.
While once you have a maquette or a model.
I see.
Like,
yeah. Right, continue. Did I interrupt you?
No, that was all.
Okay, well, I think both of these answers are in the right direction. Basically trying to, instead of having to build your large building, you can see already how the structure works as a whole in a much smaller version, or maybe look at how light, how it looks in different lighting conditions, for example. But it's basically to replace a much larger, much more complicated system with a much more reduced, smaller system. So this is an example from architecture. Let's move in a direction that's going a little closer to the field that we're going to be studying. So now, was there
yeah? someone in the chat requests to?
Oh yeah,
there's several answers in the chat.
Yes. Okay. Oh wow, great. There's a lot of having a simplified aspect of the project to start thinking of it. Yeah, that's a good one too. So you could build a model as part of your the beginning of a much more complicated endeavor. Planning the final built result, exactly. Capturing the most important components of a system. I quite like that as a mathematician. Finding potential flaws, exactly. Manipulate things that are technically easier to manipulate. This is all perfect. Yeah, so you guys are basically on this. And now let's, so think now about model organisms. I mean, if you guys want to just write out some model organisms in the chat now that I'm looking at it, throw any out. You don't have to. Maybe I'm being too interactive. Rats, yes, perfect. Well, I had mice. C. elegans, yes, I don't have that picture though. Primates, okay, I've got rats and, well, I have mice, I have rodents. So here's a mouse doing a virtual reality decision-making task. And because I study mice, that's why I put this first. And the reason that we study mice, well, some people would argue, is not because we care about mice, but we care about humans, or how humans would solve these behavioral tasks. Someone else pointed out primates. Someone says ferrets, which unfortunately I didn't include an example of this. I should have given LSP. But yes, so there's primates, monkeys, much closer to human behavior. And then on the other hand, there's also flies, right? Or much more simple organisms. You can think of C. elegans too, somebody said that. Or maybe larval zebrafish as well. And really what I want you to get from this is that there's a range of different model organisms that you can use to study the same type of, let's say, decision-making behavior, following a range from having more sophisticated, more human-like organisms to organisms that are more accessible and more controllable. Obviously, a fly doesn't quite have the same cognitive abilities as a human or even a primate, but they're much more genetically controllable. And they breed a lot faster, so you can do experiments much faster. They're more tractable in a way. So none of these organisms is correct in particular, but they all have different cost benefit associated with studying them. So now I have this really annoying dialogue that I would like to invite two people to read. Anyone want to volunteer for this?
I'll do it.
Okay, do you want to be blue or black?
Whatever.
All right, will you be black? Because I'm afraid there won't be any more volunteers. Anyone want to do the easy blue part? If not, I will do
I'll
it.
use the blue part.
Okay, great. Great, all right, you guys go for it.
What a useful thing a pocket map is.
That's another thing we've learned from your nation, map making, but we've carried it much farther than you. Would you consider the largest map that would be really useful?
About 6 inches to the mile.
Only 6 inches? We very soon got to 6 yards to the mile. Then we tried 100 yards to the mile. And then came the grandest idea of all. We actually made a map of the country on the scale of a mile to the mile.
Have you used it much?
It has never been spread out yet. The farmers objected. They said it would cover the whole country and shut out the sunlight. So we now use the country itself as its own map, and I assure you it does nearly as well.
Okay, so this is a kind of amusing passage from a Lewis Carroll story. So anyone want to tell me why I made you read it? You can also write in the chat if you want. What is the point of this?
Because the whole point of the model is to make something a simplification of the actual thing you're trying to understand. Otherwise, you may as well use the actual thing itself.
Yeah, exactly. So what makes a model useful? So I hope I convinced you with this kind of funny anecdote that it's not necessarily having more detail. So there's a very famous quote from George Box, the statistician, that all models are wrong, but some of them are useful. And so this example of maps, so of course, if you have a map that's a one-to-one scale, that wouldn't have any utility for the actual, for understanding the system, because it's as complicated as the system. So then the question is, how much detail do you include? And there's, it's not really an easy question to answer. I'm sure you will hear about Mars levels in many of your other lectures, so I decided not to go over that. But here's a very nice, does somebody have access to this, to highlighting? Who's highlighting that? Okay. All right, well, this might get very interesting very fast if you guys have access to annotations. All right, yeah, so how much detail should you include? It really depends on the question that you're trying to solve. So the same model can be either good or bad in different contexts. So a good example of this is Newtonian mechanics, which is very useful for understanding how planets move in the solar system. But not useful when you want to include relativistic effects, right? So it's not necessarily that Newtonian mechanics is a bad model, and that's why we still learn it when you learn physics today. But it is a, it does depend on the question that you're asking. If you're just interested in like classical physics, then it's not necessarily a problem. Okay, so what other things make models useful? Well, in some ways you could say that science progresses through successive wrong models or updating models that are wrong. If we take this quote from George Box seriously, that all models are wrong, then it must be the case that science progresses by going through various wrong models. And so the example of this is scientific paradigms, like in Thomas Kuhn's work, The Structure of Scientific Revolutions. He posits that science basically works by having a particular paradigm that you use to understand a particular system. And then scientists work within this paradigm or within this model until it's not able to explain some particular feature of the external world, and then they have to update that model. And that process of finding something that can't be described by that model and then updating it is essentially how science works. Models can also be useful for proposing mechanisms, and a good example of this is the DNA double helix, where they propose the structure of DNA using their model, their conceptual model. Example, Watson-Crick. And also, I'd like to think of models as metaphors. So, for example, it kind of helps you to bring intuition from another field or another system to understand a complex system. So one example is Freud's theory of psychological pressure that's using kind of a hydraulic metaphor to understand the inner psyche. Another example is mathematical models, which is describing some kind of empirical phenomenon using a mathematical type metaphor. And by doing that, then you can use intuition from mathematics and from physics that you've developed for those types of equations in order to understand that particular phenomenon, even though your mathematical model is not exactly the same as that phenomenon that you're studying. Okay, so why mathematical models? So they use intuition from math and physics. They can also be very useful for predicting behavior of very complex systems based on very simple mathematical rules. An example of this is in weather forecasting, where there are very simple rules based on pressure and the local physics, and then you can do modeling to see how the climate changes, or agent-based modeling is another example of this. So that's another reason why you might want to use a mathematical or a computational model. Also, they can make predictions that can be used to falsify theories. So one of the best examples of this is Paul Dirac's prediction of the positron, based on the mathematics that he wrote out, predicting the existence of a particle. I mean, quite phenomenal, actually. So the motto of this class is going to be, "What I cannot create, I do not understand." This is the words of Feynman, and this is a picture of his whiteboard at the time of his death. You can see it up here. "What I cannot create, I do not understand." And so hopefully I've convinced you why you should be taking this class, although I guess if you're here, I didn't need to convince you that much. Okay, so let's go to the third point, an overview of the course and also the Moodle website. So here's the lecture plan for the course. So today I'll talk about the origins of cognitive modeling. Then I'm going to go into neural excitability, so what makes a neuron spike, the biophysics of that. Then I'll go on to more functional ideas of neural coding, then visual perception, both in a bottom-up and a top-down framework, and we'll use that as a model of perception in general. Then uncertainty and confidence, that's going to be like Bayesian brain type hypothesis. Decision-making, very classic. Reinforcement learning, a very powerful way to understand behavior. Memory, language, intuitive systems, evolution of social behavior using evolutionary game theory, and finally collective behaviors, hopefully with a case study in COVID. We'll see how that works out. So as you can probably see, this is a very broad range of topics. And so I'm really going to be asking you in this course to be interested in many things. It's pretty much guaranteed that the majority of this course is going to be about subjects that you're not fundamentally interested in because it's so broad. But hopefully you will be able to appreciate what links all of these together. All right, so let's talk about some of the actual course information. So I guess you've noticed by now that the language is in English. So I'm going to be doing all the lecturing in English, all the assignments in English. All the homeworks need to be submitted in English. If this is a problem for you, DeepL and Google Translate work pretty well, honestly. I'm not going to take off points for grammatical errors, although if you do this and then you translate, please do look through to make sure that it makes sense, just to save me a little extra work trying to understand. I mean, I should just be able to see to understand what you're saying, I guess. You can ask questions in French. I may not be able to understand them, I may or may not, but we'll figure something out, someone else will translate. I mean, don't let that be an impediment, basically, if you don't understand something, or if you want to make a point. We'll figure out a way to work around that. The course website is Moodle, not Schoology. So sorry to those who already joined Schoology, and sorry to those who were not able to join Moodle, which was the vast majority of you. It seems that there were some problems with the registration. So to self-enroll, so if you haven't already tried doing this, please try to self-enroll as a student. The enrollment key is Pandemonium. Does anyone know why I chose this as the enrollment key? Any chance?
It's a very famous connectionist model.
Yes, very well done. And you'll learn about it in the 4th lecture. Great. Okay. It's not because it's chaos of demons. All right. If you have any problems with actually getting into Moodle, like signing in, then contact Natalie Thomas, because I don't have that type of administrative privilege. If you have any problems with after you've signed in successfully, but then problems like accessing the course or enrolling as a student rather than a guest, then email me. And so I'm going to use Moodle for accessing and submitting assignments, quizzes, lecture slides, etc. Hopefully, assuming that we're able to sort out these issues in the next week. Also, please use Moodle to contact me to ask questions, because if you send me an email, I'll probably lose it just because I get so many emails. So Moodle is the best place to start. And then if I don't respond, or if it's really time sensitive, you can email me. I'll make all course material available on Tuesday at 5 or at 7, depending. So today I'll put the lectures up immediately after. So a question about the math level of this course. It seems like you were all pretty comfortable, at least with algebra, which is a good sign. There will be basic math in lectures, but there will actually be no algebra, so I'm not going to I mean, you should understand what the equation means, but I'm not going to ask you to manipulate it either within the lecture or in your homeworks. This is not a math class. And again, the quizzes and exams will not require any math. So what is there? Other than the math, there are the ideas, and that's essentially what we're going to be discussing. All right, were there any questions on that? On basic info before I get to the evaluation? Okay, so for the evaluation of the class, so 10% of your grade will be weekly quizzes. The reason I'm doing this is to help you consolidate information. These are not meant to be very difficult quizzes. They're just meant to help you kind of consolidate the information that you learned from the lecture, and also to see what types of ideas I find to be the most important, which will help you for the exam, of course. So these are going to be on Moodle, and they're open book in the sense that you can use your notes and you can use the lecture slides. But obviously you can't use each other. So don't, obviously you have to do this by yourself. And don't post questions on Stack Exchange. But you can use other resources. It's timed, so there's 10 questions and there'll be 15 minutes. So the reason for this is so that you don't really have time to not pay attention in class and then look everything up as you go through the quiz. So it's you won't have enough time to find everything in the slides in order to do this. And it's going to be available at 5 p.m. on Tuesday and due at 5 p.m. the next day. So you have 24 hours to do it. You can start it at any time in that 24-hour period. That's really to help you, trying to force you to do this right when the information is fresh in your mind. There's one exception for this week because Moodle doesn't seem to be working very well for many people. So this week is just due the next class. So next Tuesday at 5 p.m. And the lowest grade is going to be dropped. This is because I anticipate, since there's such a time pressure, that sometimes someone's going to have something that comes up in the 24 hours after a class. And so you don't have to ask for an extension. You'll just automatically have the lowest grade dropped. Are there any questions on the quizzes? Okay. Okay, so then you also have homework assignments. This is 40%, and this is more for critical thinking. Before I had put weekly homework assignments, but I actually think that's probably too much. So I've changed it to bi-weekly assignments. So the way this is going to work is that I'm going to assign a reading every week, and I recommend that you do it every week, but it's not going to be assessed every week. Instead, I'm going to ask you to send me a written response every 2 weeks. So for every even numbered class, you'll get a choice of responding to the reading from the previous or the one before that, basically. And you can choose which of the ones you want to respond to. There's a 300 word limit, and that's baked into Moodle, so you can't like make margins smaller or I guess bigger. You can't make margins bigger or like change the font size. It will stop you after 300 words. The reason for this is because I really want you to do some critical thinking, basically state your opinion and back up why you have that opinion in a way that is very succinct. So submitting this via Moodle, and do not summarize, please. I'll give you a lower grade if you just summarize the material, but I really want, so all the readings basically are going to be kind of like reviews or maybe debates about different ideas covered in the class. So I really want to know how you've engaged with this material, what you think about it. They're not debates that have a right or wrong answer, and don't feel like you have to say what you think I would want to say. I really want to hear, I really want to see some critical thinking on your side. And the deadline will be Tuesday at 5 every 2 weeks. But the readings will come out every week with the rest of the lecture materials. Any questions about the homework assignments?
Do you hear me?
Yes.
We need to relate the text and our courses in the way we want.
Yeah, so I have some, so for every reading, I have some proposed questions that you should be thinking about. That's really mostly to guide you if you feel like you're not sure what you're supposed to be getting out of it. You don't need to respond to those questions. You could, if you find something else that you find interesting, like a big picture thing, not like a very small detail in the reading. I mean, I think you can ask me as well if there's some particular thing that you want to respond to and you're not sure if that's okay. You can ask me through the Moodle website.
Okay, thank you.
Is the first of these homework assignments due on 2 weeks from today, the 6th of October?
Yes, yeah. It's due a week after the second lecture. Yeah.
And
are we going to have some like schedule, or so it's on us to keep an account of what week is odd, what week is even?
So on the Moodle website, they'll have the assignments. I'll also mention it in class, but it's every even lecture. Then that's when you have to decide between the two. But basically, what it means is that in the folders for the even lectures, I'll just put an assignment. So if there's no assignment, you don't have to do anything. If there's assignment, that, yeah. Anything else?
Yes, I wondered, will we have some time to sort of discuss these papers in the class? If they're sort of open-ended debate questions, it might be interesting for us all to share our opinions.
So I'm not, okay, so here's, I should have said this at the beginning. This class is a complete experiment. So I hope there will be, if there's time, we'll see how fast this class goes. If there's time, then I'll try to like have a little bit of time at the beginning of like the next class for people to talk about the ideas. I think that would be really fun. If not, then I think, so would it be useful maybe if I showed you the Moodle, what I put in the Moodle website for like a couple minutes? Because I put a forum where you could talk about the ideas of the classes. You can do it online basically. Dory Guzman says both. Does that mean you want to have both in-person discussions and online discussions? Oh, no, that was a response. Okay. What time is it? 36. Okay, I'm going to go through the class, and if we have time afterwards, then I'll show you around Moodle. But we should get going.
Just to follow up though, sorry.
Yeah,
please. Is this the 0th class or the first class?
No, this is the first class. So
okay.
It's on the slides. Yeah, it's a good question.
Because
there.
In even number classes then would be, there's a writing assignment due the next lecture, like in a week from today?
So there's this week, there's Origins of Cognitive Modeling. And then next week, there's Neural Excitability. And then the third week, at the start of that lecture, your first assignment will be due. And then we're going to move on to the next 2 lectures. Is that clear?
That is very clear. Thank you.
Great.
There's a slight problem with the screen sharing.
Let's speak. I see. Can you? Is this working?
Yeah,
what are you? Yeah.
It's like intermittent. It goes black from time to time.
Oh, is that happening for other people too?
Not for me.
Why don't you? Can you use the nonverbal communication so I can get like a rough fraction of people to say yes if it's not a problem, if it is a problem, and no if it's not?
Must be my connection then.
Yeah, it seems like it's mostly. All right, this is so cool. All right. Okay, any more questions about the homeworks? Okay. All right, so that's half the class, and the other half the class is going to be a final exam. Honestly, the details are going to be highly dependent on what happens with the pandemic. So I'll tell you with good preparation. But what I'm envisioning now is that you'll basically have a mixture of multiple choice questions like the quizzes and a mixture of more kind of short essay questions like the homeworks. Actually, how that's going to work is it can be very COVID dependent. Okay, any questions on, I didn't give you that much information, but any questions on this in general before I move on to the lecture? Okay, great. So let's move on to the final part, Origins of Cognitive Modeling. It's been a very old question, how the brain and the mind are related. And this is a question, I guess, that we're going to tackle in this class in some sense. There are many different ways of thinking about this. So there's kind of dualist point of views that mind and brain are two fundamentally different types of thing in the universe, that the universe is made into these two substances. And then there's the more monism view that is either, if you're an idealist, it's just all mind that then gives rise to matter. If you're a materialist, it's matter that then gives rise to mind. And that's the position that we're going to take in this class. So there's been a very long history of trying to understand how the brain gives rise to the mind. So I just want to give you kind of a historical background about this. So if you go back to the ancient Greeks, there are these hydraulic metaphors. So Hippocrates had these ideas of four humors, and these were liquids that then in different concentrations determined your personality. Descartes had this idea of animal spirits that were liquids that, in this example, L'Homme de Descartes, could create like a physical movement in response to some kind of sensation, like a fire in this case. And the more modern interpretation of this was by Freud with psychoanalysis and this idea of mental pressures. So this is just a class of hydraulic metaphors that kind of started with the ancient Greeks. Going on from that, there are these mechanical metaphors that you're probably familiar with, these ideas of automatons. And so this was really put forward by Lemaitre and L'Homme Machine, that man is a machine or man is an automaton. There's this example of a mechanical Turk that was basically an automaton that played chess, turned out to actually be a guy hiding in this big box, but it apparently fooled a lot of people for a while. And then more recently, Sherrington's idea of the brain as an enchanted loom. These are all different metaphors of the brain in a mechanical sense. And going on more modern still, there's electric communication metaphors. So von Helmholtz had this idea of signaling between different neurons as being like a telegraph. And then McKay and McCulloch had this idea of signal transmission, again, from electronics, how different neurons signal to each other. And the more modern ones that you're probably more familiar with are computer metaphors. So this dates back to McCulloch and Pitts, and that's what I'm going to start to discuss later in this lecture. And I think you could argue that there's a new metaphor that is coming out now that is deep neural networks, or some kind of artificial intelligence metaphor. And I think that's because it's quite different from how we usually think about kind of more computer-based metaphors of how the brain works. But maybe this is something we can argue about later. Windmill Leibniz. This is not one that I know. I guess this is a mechanical metaphor for the mind. Is that right, Hook? Yes. Okay. All right, great. Maybe I'll include that for next year. Okay, so the reason I'm showing you this is to show you that basically all of these ideas about how the brain works are based on these metaphors that were based on powerful technologies at the time, technologies that were revolutionary. So going back hydraulic from the ancient Greeks, then mechanical, more Victorian era, and then more recently with electronic and computer metaphors. And so the models that I'm going to show you in this class are going to be from these two groups of computer metaphors and deep neural networks or artificial intelligence metaphors. And I just want you to keep that in mind, that we are studying kind of a paradigm of how the brain works or how the mind works that is not necessarily the only one that you can think of as possibly a historically particular view of how the brain works. And with that, I'll start with McCulloch and Pitts. So this was a very influential paper from 1943 that really kicked off this kind of computational mind train of thought. So here, this you can see from, I think, just the title. The title of this paper is A Logical Calculus of the Ideas Immanent in Nervous Activity. So logical calculus, really trying to understand the logic of human reasoning, the ideas immanent, so understand the mind, in nervous activity through principles of neural activity, of electrical signaling between neurons. So McCulloch and Pitts were influenced by two very famous groups of work themselves. The first one is the Principia Mathematica. This was written from around 1910 to 1913 by Bertrand Russell and Alfred North Whitehead, who were two mathematician, logician, analytic philosophers. And they wrote this huge tome, 3 volumes, that was an attempt to express mathematics using the minimal assumptions possible, so the most basic axioms that they could think of, and formal propositional logic. So they were really trying to build up all of modern mathematics from this really basic propositional logic. One of the main reasons that they wanted to do this was to avoid paradoxes that were starting to creep up in mathematics at the time. So there's this famous Bertrand Russell's paradox. You have a town in which every man shaves himself, but who shaves the barber, or something like that. So they were basically trying to avoid these types of logical paradoxes that you get from set theory, essentially, from really basic types of mathematics. And here's a page of what that looks like. So you can see it's very, very logical, symbolic, kind of abstract writing, which shows you how fundamental they were trying to get. And I don't know if you can read at the bottom what this says, but the line is, from this proposition, it will follow, when arithmetical addition has been defined, that 1 + 1 is equal to 2. So the kind of famous factoid about the Principia Mathematica is that it takes over 300 pages in this tome just to prove that 1 + 1 = 2. I'm just trying to give you an idea of like how fundamental, how rigorous they were trying to be when developing this. Ultimately, it was a flawed endeavor for some very interesting reasons that are not related to this course, but if you are interested, you should read Logicomics, which is a graphic novel about Bertrand Russell's life, and it is really cool. But ultimately, they were not successful because there were some more fundamental problems in mathematics, let's say. Okay, so this is the first body of work that inspired McCulloch-Pitts, and the second body is the Turing machine. So this was a bit later, 1936, by Alan Turing, modern hero of computational science. So Turing devised this idea of a Turing machine, essentially an automaton that manipulates symbols in order to, in specific rules in order to solve some kind of algorithm. So here's an example of a Turing machine. I mean, it's not a machine in the sense that you would actually build it, although some people have built at least approximations to Turing machines, more of a kind of a conceptual idea. So the main parts of a Turing machine are basically you have an infinite tape that has some kind of finite symbolic alphabet. And here, this is a binary alphabet, so there's only 0s and 1s. The second part is that you have a tape head. Can you see my marker, my pointer? Yeah? Okay. And this tape head can do a few things. So it can read and write. So it can read that this symbol at this position is a 1. Or it can overwrite it, so it can write it to a 0. Or it can move left or right along the tape, or it can stay in the same position. And which of these things it does is based on some rules that you can define for the machine based on like the particular algorithm that you want to compute and the particular state or the letter that you're viewing at that particular time. And so what Turing showed by developing this idea is that you can design a particular Turing machine in order to perform a particular algorithm. So an algorithm like squaring a number, for example. So your input is any number and your output should be a squared version of that number, something you can do with a Turing machine. Or if you want to do some other algorithm, I'm trying to think of a non-mathematical one. Maybe you have a list, you have some different input, the inputs are some different symbols, and you find the one that is not matching of the other ones or something like that. So any algorithm that you can think of, you can design a particular Turing machine in order to perform it. But the thing that was really quite remarkable is that you could also define something called a universal Turing machine. And this is a single machine that can implement any other Turing machine. That means that it can implement any other algorithm. So you don't have Turing machine 1 for algorithm 1, Turing machine 2 for algorithm 2, Turing machine 3 for algorithm 3. You have a universal Turing machine that can perform algorithm 1, algorithm 2, algorithm 3. And does anyone have an idea about how this can be, how you can do this? It's kind of not fair because it's all in the slide. I didn't bother to, to remove it. Anyone want to guess or read from the slide?
So yeah, one part of the code is devoted to coding a Turing machine that will take in charge of the rest of the code.
Yeah, so the trick basically, as you said, is that you have basically the instructions for what Turing machine you want to perform in the input. So before you would only have input of the Turing machine and the output, and now part of the input is also, let's say like a code number that tells you which algorithm to perform. So that'll tell you in this example, like, yeah, here are different rules for different algorithms. So basically, the idea, this was very influential because, well, first of all, inspiration for modern computers. If you think about it, a computer is a machine that can perform not only like calculations, like a calculator. It can do what a calculator does, what a word processor does, et cetera. It can do all of these functions in one machine. They were directly inspired by this idea of having a universal machine that can perform any algorithm with the Turing machine. Okay. So these were the two main pieces of work that really inspired McCulloch-Pitts. And this is the logical flow. So stop me if it's not making sense of how it influenced them. So first, this was their assumption. And I think this is up to debate. Actually, it is up to debate. We can debate it if somebody wants to. But they argued that propositional logic is the basis of rational thought. So when you're thinking of cognition, they were really thinking of reasoning, of human reasoning. This is not actually how we think about cognition today anymore. But at the time, this was the predominant way to think about what it means to think. So good example of this is modus ponens, or deductive reasoning. Socrates is a man. All men are mortal, therefore Socrates is mortal.
But this isn't actually propositional logic, the example.
This is propositional logic. What do you mean?
It's more predicate. It's predicate logic.
I'm not a logician. I thought
it's
this was
first order logic. First order.
First order logic. What's the difference?
Yeah. In first order logic, you can also use predicates, because in propositional logic, there are only sentences as wholes that are used.
Okay. All right. Well, all right. So maybe there's a little bit of a technicality, whether it's predicate or propositional logic. Anyway, let's say logic is the basis of rational thought. All right. Is that good enough? Okay. All right. Okay. So first of all, there was the Principia Mathematica, which showed that a lot of complex logic in mathematics can be derived from basic propositions using this very formal type of logic, using the symbolic language. So that was the first important step in this thought process. The second is that with Turing, he showed that with binary symbols, you can construct a universal computing machine that can perform almost any algorithm. And so if you put these together, that rational thought is something like symbolic, similar to mathematics, which you can derive using these kind of basic manipulations of a symbolic language, and that you can construct a universal computing machine that uses those binary symbols to perform any of those algorithms to do that type of manipulation, then maybe neurons in the brain can be those binary symbols that can be manipulated, and that's what produces thought. This is basically their argument. And so they hypothesized that a neuron can act as a truth statement. So I'll give you kind of was there any questions about that line of reasoning? No? Yes? Okay. Okay, so we need to get in the mindset of McCulloch and Pitts. Think of a neuron as a truth statement. So there are three really basic parts of a neuron, kind of smoothing over a lot of technicalities. So there's the dendrites, which receive input from other neurons. There's the soma, which is the middle of the neuron center, the cell body, which processes those inputs. And then there is the axon, which sends that information or those signals to other neurons. And so the way that neurons send information to other neurons is by generating electrical signals that are called action potentials or sometimes spikes. Those are like these very fast fluctuations in the membrane potential. So this axis is voltage and this axis is time, and they move in the direction along the axon to the downstream neurons. These are all or none events. So they either happen, when we say that it spikes, or it doesn't. And because they're all or none, that's where McCulloch and Pitts linked this to basically the truth value of a particular proposition. So if the neuron spikes, then the truth value of that proposition that that neuron represents is 1, or it's true. And if it doesn't spike, then it's false. So yeah, so neurons can represent the truth value of the statement. Another basic fact, again, smoothing over a lot of biological detail, is that in order to generate one of these action potentials or one of these spikes, the input has to be greater than some intrinsic threshold. And that threshold depends on the neuron. And so what kind of inputs do neurons get? They get input from other neurons that they receive on their dendrites, which are action potentials that are transmitted from other neurons. And those connections between one neuron and another have a particular weight, which is essentially a factor that multiplies the strength of that particular input. Any questions? Is this clear? Okay. So let's look at how can you build a logic gate with neurons. So here, X1 represents neuron 1 and X2 represents neuron 2. And we're going to have a downstream neuron Y that is receiving input from both X1 and X2. And this neuron is going to have a threshold of 2. So in other words, it's going to be active, it's going to spike or have an action potential if the input is greater than or equal to 2. And it is going to be inactive if the input is less than 2. So let's see what happens if you have various different inputs. I should say also these, so these are different statements in logic according to McCulloch and Pitts. So maybe X1 represents Socrates as a man and X2 is all men are mortal. Okay, and we'll say that first let's assume that the weights are 1 for the sake of simplicity on each of these. Okay, so I'm going to build a little truth table. So X1 is 0, X1 is 1, X2 is 0, X2 is 1. And in each of these cases, we're going to put the answer. So the values for Y are going to go into each of these 4 locations. Okay, so what happens if X1 and X2 are both 0? Then you have 0 times your multiplicative factor 1 is 0. 0 times your other multiplicative factor 1 is 0. So you have 0 plus 0, so Y is 0. Okay, what happens if you have X1 is 1 and X2 is 0? Does anyone want to guess?
0.
0, yes, exactly. And then the same if you have X1 is 0 and X2 is 1 is 0. And if they're both 1, then you sum them, you get 2. And that is yeah, and then that's 2, which is greater than or equal to the threshold, so that neuron Y is active in that case. So does anyone want to, like, what is this the truth table for?
And
great. Yes, this is X1 and X2, right? So this is basically how you can have a logic gate out of these like very simple rules. You can do the same thing for, so then your Y is Socrates is a man and all men are moral, using this assumption from this logic. Okay, so here's another example where I've increased the weights to 2. Does anyone want to first guess what they think this logic gate is?
Or.
Yeah, this is or. So to make this clear, if you have 0 and 0, you multiply by 2 and you add them, you still get 0. So there's no activity for neuron Y. If you have x1 is 1 and x2 is 0, then you have 2 times 1 plus 2 times 0, which is 2. So the neuron spikes, so you have a 1. If you have x1 is 0 and x2 is 1, that's the same. Since the weights here are the same, then you again get a 1. And if they're both 1, then the input is even larger, so you have 1. So yeah, this is an example of x1 or x2. So in this case, this Y would represent all men are mortal, or Socrates is a man, or all men are mortal. Are there, what the weights are?
Quick question.
Yeah.
Is there a reason why you would change the weights and not the threshold, or is it equivalent?
There's an equivalency there. I mean, if you increase the threshold by 2 or if you decrease the weights by 2, it's the same. You have extra freedom in changing the weights because you can change them differently. So basically, if you change the threshold, that's equivalent to changing the weights in the uniformly in the other direction.
Yeah. Okay.
Yeah. So Charlotte asked, I didn't get what were the weights in the last slide. I'm not sure what the last slide is, but basically the weights for the purpose of this lecture are a multiplicative factor that changes how strong the input is, how much it affects the downstream neuron. In terms of the neurobiology, I mean, there's a lot of different factors that can go into this about the details of how neurons release the neurotransmitter or how likely it is that there is a neurotransmitter to be released. I mean, there's a lot of different factors that affect the weights. Is this answering your question? I wasn't sure if this meant like biologically or in terms of the law. Okay, great. Okay. All right, so we have one more example. Oh, darn, I should have made you guys guess this. All right, but okay, here's another example where if you make one of the weights inhibitory, meaning the weight is negative, so that means that it makes it harder for the downstream neuron to spike, then you can get an X1 and not X2. So this is quite exciting, I think, if you really had this idea that all of thought was like this kind of symbolic manipulation. And you kind of piece together these different facts. I really can't overstate it enough. The big picture of this is that McCulloch and Pitts showed that you can, using these very simple assumptions about neurons that are in a really rough, broad sense in line with the biology, at least to first order approximation, then you can compute these logical operations like and, or, and not, etc. And that this could then form the basis of mental thought and deductive reasoning. And I'm really not overstating this. Like, this is a line in their paper. Thus, both the formal and the final aspects of that activity which we want to call mental are rigorously deducible from present neurophysiology. Quite a bold claim. This has also been called the paper that killed dualism. To be fair, I think it was by one of McCulloch's students later. So not entirely impartial. But yeah, this is the big picture of connecting really these really basic neurobiological principles to this idea of having a logic of mental thought. All right. Any questions so far?
It seems unlikely that weights physiologically would be, integer values, and also there's a lot of stochasticity to like whether an action potential will fire, and it seems like most of the time any given sort of tiny network of neurons won't actually implement a meaningful logic gate. So how, like, does that make sense? Like if the weight were, if the weights in this AND example were, rather than 1 and 1, 1 and 0.9, what does that mean? That's not really an AND gate.
Yeah, well, I guess you could, you're finished, sorry, did I interrupt you? Okay,
No,
you could, I mean, you could argue that like the threshold is somehow adjusted to this. I mean, really they were kind of coming with this idea that everything was like hardwired in some particular way. You have this like very fine structure that had to be hardwired into the brain. And so you're right that this doesn't work very well with what we know now about like the stochasticity of like ion channels and neurotransmitter release, at least. I think it's another question whether there are other types of like circuit level stochasticity in the brain. But I don't think the integer values are a problem as long as you have they don't need to be integers as long as everything is very finely tuned, right? But the stochasticity is certainly a problem.
I mean, even in modern computers, you've got some kind of stochasticity that is afterwards corrected by correction systems. So like a 0 or a 1 might fail, but it can be corrected afterwards. So I don't think it could be that much counter argument to this theory.
Yeah,
that's a good point. I guess there's like, oh, sorry, do you want to go
Well,
ahead?
yeah, my point isn't, it's not so much even about the stochasticity. I mean, because I appreciate that. So in the case of like a transistor, you can have the same, whatever current going to the base and the collector and whatever. And so you'll have it's sort of standardized in such a way that even though there's stochasticity, like the transistor is doing the same thing every time. But I'm saying because like neural connections are different every time slightly, and so it doesn't seem likely that in any case there would even be something resembling an AND gate. It seems way more likely that there'd be some sort of nebulous, not really meaningful half logic that on a big scale, like on a emergent scale or on a population level, is doing something meaningful, but at the scale that they're talking about, it just doesn't seem likely. Like, how could weights be exactly the same? Because I see what you're saying, it doesn't need to be an integer, but if it's finely tuned, that just doesn't seem possible.
Yeah, this is, again, like a very historically particular view that they had at this time. Of course, now, nobody believes that this is happening in the brain. But it's very important to think about, like, in terms of the origins of how modeling the brain and the mind started. And I think it's important to know what that legacy comes from. But you're absolutely right that now nobody really thinks that this is a viable, yeah. So this is why this is the origins of cognitive modeling, not the today of cognitive modeling, right? And actually this leads exactly, oh, it doesn't, I forgot I had this, sorry. It leads in the next slide to what you were saying. All right, so this, okay, so one of the reasons this was really important beyond cognitive science or beyond neuroscience is it also really inspired artificial intelligence. So this is the Dartmouth Summer School, which happened in 1956, which was basically a workshop that is widely considered to be the event that started the field of AI. This is, it was organized by John McCarthy, who's in this picture here. and who you will see in your reading. And he essentially, he was the one who coined the term artificial intelligence for this workshop. And there's also McCulloch, who I think is here, although he doesn't have his beard, from McCulloch Pitts, as well as Marvin Minsky, who's going to show up later, who's right here. So some really of the giants in this kind of this field. And so at the time, they were all using these methods that were basically using symbolic logic to mimic human reasoning, similar to McCulloch and Pitts. So it's very inspired by McCulloch Pitts. And then, as Hoke was saying, there's a big problem with this, which is that it essentially requires very fine-tuned connectivity that we know at the moment now is not very likely in the brain. So how is the brain supposed to actually figure out how to build these very specific, very fine-tuned networks? So one answer is this idea of synaptic plasticity, which was predicted by Donald Hebb in 1949. So synaptic plasticity means that the connection weights that I was describing before are not constant, but they change over learning. This was later proven in experiments, which is pretty cool, to first predict it and then have it later verified. And we'll talk about plasticity a little bit more in a different lecture from a more biological point of view. But for the purpose of this talk on the origins of cognitive modeling, just the idea that weights could change and that could help the brain or an algorithm learn how to perform a particular function is what is important. So the question is, could synaptic plasticity solve this problem of how the brain can learn different functions? And this was essentially the idea of the perceptron, which was in 1958. Does anyone know what a perceptron is?
It's kind of like a primitive neural network. Like a...
Yeah, primitive neural network.
Yeah, it's like something that will linearly sum inputs, and when they sum above a threshold, it will fire.
Yep, exactly. Cyan also says a basic neural network able to learn linear separations. That's right. So hopefully, for those of you who don't know what it is, this will become clear to you in the next few slides. But the perceptron was also a physical computer that was actually created by Frank Rosenblatt. So here's a picture of one of the original perceptrons. And he was really inspired by how the brain learns, or how he thought the brain learns from childhood. So here's a New York Times article, New Navy device learns by doing. It's really funny. Psychologist shows embryo of computer designed to read and grow wiser. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its own existence. Also, it says that it only costs $100,000, so I guess some things have really changed from 1958. So the basic structure of a perceptron originally was supposed to mimic the kind of organization of the biological brain at the kind of grander scale. So basically, if you're thinking about how an organism would have a particular movement in response to something that it sees, for example. So here you would think there's the retina, and there's a projection from the retina, which is the back of the eye, to kind of an earlier sensory area of the brain. And that is a projection that largely maintains the topography, which just means like the location of where the image is. And then there are some random connections from there onto an association layer. So that's higher, basically a higher up region of the cortex that eventually is projected to the motor cortex, which will control the movement. And these particular red weights here would be plastic. And so the organism would learn that in response to a particular type of object that it sees or a particular visual stimulus, that it then raises its left arm because it's, the weights have been learned in order for it to do that. And speaking of raising an arm, Nolan has a question.
Yeah, I don't understand how the connections between the projection area and the association area can be random. Like, how do we have a result if the connections are random?
Well, that's kind of an assumption that they had at the time, and that you can have as well in the, so what are you, you're asking how can you learn based on this, if you have these random connections, is that you're asking?
Yeah, I understand how we cannot be organized. How the connection can be.
How can not be organized? Do you mean biologically speaking, or do you mean in terms of the actual algorithm that's computing?
Both.
Well, so depending on what algorithm you're doing, it can actually be very useful to have random connections. That's an active field of research, especially if you're increasing the size from like a smaller number of neurons to a larger number of neurons. You can show that that kind of projection into a larger number of neurons is projecting the input space into a higher dimensional space. That's better for downstream associative learning. So actually, like mathematically speaking, it can be much better for you to have random connections in some cases, depending on like the type of, I mean, that's made with the assumption that you want to learn arbitrary kind of classifications. You can also think about this as maybe those random connections are, this is a really old idea from David Marr, that then in this association area, each of these like neurons would then be responding not to a single type of input, but some kind of combination of different inputs. And so then you would have like this combinatorial expansion that you could then do some kind of learning based on combinations of different visual stimuli or combinations of stimuli of different modalities like visual and auditory. So that's another way that could be useful talking about the algorithm. Biologically speaking, I think I mean, certainly in some ways it's a little difficult to imagine that it could be purely random, because you think that like with axonal growth that it should be directed into some particular area genetically or something. But maybe if there's just some probability of random pruning, then that could give you, you know, random deletion of those connections. That could give you some kind of random projection.
Okay, thanks.
Okay, great. Any other questions? Okay, so yeah, so this is the, on the top is the, or this is from one of these papers, I forgot to say. This is the Organization of Biological Brain, and on the bottom, this is the organization of a perceptron as he originally defined it. So you have like the projection from, he says, sensory points that project in kind of a one-to-one way to an intermediate layer. And then there's random projections onto association system, just like he was saying previously in the projection area to association area. And then you have some response units. So these are the motor units that read out from the association system, and those these connections in red will be plastic. Plastic meaning that they change over learning. Really what we talk about today when we say perceptron is we ignore all of the rest of it and we just look at this part of it from the association system to the response units. In order to train it, so this, one way that you can train perceptrons is using supervised learning. So here's an example of a perceptron. So it's a little bit different from the McCulloch-Pitts model, but very similar in many ways. This is a very simplified version of a neural network, as someone pointed out, both simplified from a biological neural network and simplified from the deep network as we know them now. So now you have some particular pattern of inputs, which are given by zeros and ones. And you want to find the weights in this layer in order to have the output Y give the right value. So there's some kind of target output that you want to be able to train this network to learn to produce in response to a particular pattern of input. And this is the key difference. There are many differences, but really the key one from the McCulloch-Pitts idea is that this network is learning through supervised learning, whereas McCulloch-Pitts wasn't learning at all. It was very, you had to have this like very fine-tuned type of logic gates. So you basically have the learning of the weights that are based on showing examples of correct values, and this is called labeled data in AI, and then telling the network when it is right and when it's wrong. So let's say that you want to train this network to produce y is equal to 1 in this case. So then you start with some network that has, here all the weights are the same, that's why you have the same thickness, and it gives a value of 0. And then you say that's wrong, and you can train it so that that changes the weights. And in order to do this, you would want to increase the weights. For this example, you want to increase the weights from the inputs that are giving you higher values because you want your y to have a higher value. So you would increase those weights and decrease the other weights. And then this would give you, after eventual learning, the right value. So it's supervised learning, basically like learning in elementary school, which you say, what's this letter? J, no. I, yes. Okay, so after many of these iterations, it can learn to solve the problems. Iterations with different, I'm showing one example of one pattern of inputs here, but you would do this with many, many, many different inputs. So it's ultimately the other difference with McCulloch-Pitts. This is not a logic problem, this is a classification problem. You're trying to classify different input patterns into different sets. And I'll talk about the learning algorithm in another lecture. Any questions on the supervised learning side?
Yeah, so the main mechanism is that, so I don't understand, for example, if there are many possibilities for the right answer. For example, you have this combination of weights, but there may be another combination of weights which could lead to the same same answer from the algorithm.
Mm-hmm.
So how does it choose? How, like, I know it changes weight. I don't know how it choose which weights to change. That's what I mean.
Yeah, so it's changing the weights in an incremental way in order to reduce the error of the system. So it's not finding the solution, and you're right, there is no optimal solution. If you have like a finite amount of data, there's not going to be an optimal solution. As I think that'll become clearer when we talk about like the linear separability later. I'll try to remember to point that out. But it just finds a solution that's good enough and that's close to the initial condition.
Okay, so if you have many systems, they can find different solutions, and they'll all be like if you train same, like, okay.
Yeah, exactly. Which is why it's important to hold out some of your data and then test it to generalize to make sure that you found a solution that generalizes to new data that you might get. Yeah.
Okay, thanks.
Any other questions? Backpropagation is complicated, it says Hoke, and that is true, but there's no backpropagation here because we only have one layer. So that is, and we will talk about backpropagation later. And, yeah, but for a perceptron, actually, it's very simple. What gets more complicated is in modern deep learning, you have not just, instead of just having the input and then the output, you have the input, and then you have a bunch of layers of intermediate neurons, and then the output, and you have to train all of those weights. And it's actually just comes from some like really basic calculus, but the note keeping is horrible. Any other comments or questions? All right. If anything is unclear, please don't. Please feel free to ask at any point, because I know this is a very diverse audience. Some people this might be completely new, and other people might already be implementing backpropagation in their classes. So, okay. All right, so let's look at how a perceptron would implement some of these logical operations, essentially. So the difference, again, is that now the W1 and the W2 are learned by the algorithm. So we're not prescribing them and then showing that you can get an AND gate, but you're going to learn them. And I'm going to try to illustrate this to you by representing this data. So this was the truth table that we had before for the AND gate. And this is how I'm going to show it now. So on the x-axis or x1 axis, the values of neuron 1 can be either 0 or 1. On the x2 axis, the values can also be 0 or 1. And so each possible combination of inputs, I'm going to put a dot there, and the color is going to be the value of neuron Y that we want, the target value, in order for Y to be performing an AND operation. So this is the same as here, but now I've like flipped the axes and colored them 0 to red and 1 to blue. Okay, and then if we write, remember before it was you want the sum of the inputs to be greater than some threshold. So the sum of the inputs is the weight of the first neuron times the activity of the first neuron, plus the weight of the second neuron times the activity of the second neuron. And does anyone, maybe excluding the mathematicians, kind of physicists in the room, what is this equation?
Dot product.
Sorry?
Dot product.
Yeah, so, but I was looking for something a little simpler than a dot product. Since you said dot product, I know that you're you have mathematical or physical training, so you're not allowed to answer this one. Just teasing you. Scalar product. That's not. It's not. Well, it's like a sum of scalar products, I guess, but it's really. All right. So something like really basic that you learned in high school. Okay, it's a line. It's like really not expecting people to say dot product and scalar product. Okay, so you remember from learning, at least the way I learned in high school, you had y is mx plus b, or x2 is mx1 plus b. So you arrange the terms a little bit, and that gives you a line. So this is essentially a line. And so basically what this is saying is that if the input is greater than a threshold value, then your neuron should be active. That means that if you're in this part of this space of different input possibilities, then you should have your neuron Y should be 1, and otherwise it should be 0. So basically, geometrically, this is equivalent to separating points with a line. This is also called linear classification. So Noaman had made a comment that, is there like a unique solution for this? And you can see clearly not, because you can wiggle this line very much and you would still be able to separate these points. So that kind of shows you that in general, there's usually not a, unique solution, although there's like a best solution to maximize the margin, which is the separation, like maximize the separation from the points to the line, but that's another story. Okay, any questions on how the perceptron is equivalent to separating points with a line? Because this is very, very key to understand. Okay, I will continue. Okay, so we can do this for all of the examples that I gave you. So here you have OR, so that maps onto these colors, and so there's a different line that you can use to separate the 0, 1, and that corresponds to different weights, of course. And you can do this also for the and not logical operation that I gave an example of, and you get a different line. So basically, you can kind of think of, I mean, the perceptron can essentially solve these same like logic operations that the McCulloch-Pitts neuron can solve. That's where I'm going with all of this. So there's the two important things. So first of all, the perceptron, as I was saying, is a type of linear classifier. That means, so if you're thinking so here I had an example with a larger number of input neurons before, right? And we can draw that in a higher dimensional space. So instead of having x1 and x2, well, I can only do 3 dimensions because of limitations of the human brain. I guess there are actually more, it's not limitations of the brain as much as limitations of space. Anyway, so you have neuron 1 activity, neuron 2 activity, neuron 3 activity, but you imagine if you have 100 neurons, then you would have 100 different axes in a much higher dimensional space in an abstract sense. And you have different red points and blue points, and you want to find a hyperplane. So you want to find some kind of plane that separates them. The plane is a higher dimensional extension of a line. So this is really how you should think of a perceptron, as a way to find a separation between these points using a line or a plane or a hyperplane. And in many senses, it's more general than McCulloch-Pitts. So first of all, it is not limited to performing logical operations. You could do other types of classifications. You could also have a more continuous input space. So you can use, so a classic example is MNIST, which is here on the right. So this is a data set of handwritten digits taken from US letters, the postal code, I think. And so you could use the pixels. There's actually a bad example because I think this image has been binarized, but imagine that you had a grayscale example so that the inputs wouldn't be 0 or 1, but they could be the luminance of the pixel. And very importantly, this idea about putting learning at the forefront, and especially supervised learning, gave birth to a new form of AI called connectionism. Is this this example with the higher dimensions clear to anyone? Okay, I'm losing track of the verbal feedback, so I'm going to erase it, and then if anyone finds it unclear, say no. If you find it clear, say yes. Okay.
There's a question in the chat.
Can it separate the space in more than 2 subspaces? No, but what you can do is just put more on there. So you can just put more perceptrons, and then they can separate the space into different subspaces. What's the conceptual difference between connectionism and the older one? Both are still used. Great question. And next slide, I think. Were there any other questions before I move on? I'm loving these questions, by the way. Very nice, deep questions that you guys are thinking. It's good. Okay. So yeah, connectionism, new approach to AI, and represents a different way of thinking about how cognition works, or how is knowledge represented. How is this different from the older version of AI, which is called symbolism, symbolic AI, also called GoFi, good old-fashioned AI, because it was essentially the one that came first. So at the time, it was considered old-fashioned when connectionism came about. Maybe things have changed now with the big recent push in deep learning. The basic idea of symbolic AI is that cognition is essentially symbolic manipulation, as we saw with McCulloch-Pitts, basically thinking about like deductive reasoning or knowledge, or these types of cognition. Symbolic AI has the model of the world encoded into the system. So that means that it can't really learn the structure of the world. It needs to have that structure encoded into the world. There's some problems with this approach. So for example, it's not good at handling the inherent messiness of the world because real data is not so clean. Symbolic AI is, like you saw in the McCulloch-Pitts example, has assumptions on, I mean, as we were talking about in the little discussion that followed, is not very robust to different types of like stochasticity, randomness, although maybe there is a possibility with like error correcting code, which someone mentioned slightly. But in general, it's much worse than connectionism at handling this type of stochasticity, randomness, messiness. It also requires handcrafted world knowledge. So typically you have to, and this is what I mean by the model of the world being coded, you have to put in the assumptions about kind of the structure of the world. So here's an example. Well, I put the example last, which is not great. I'm just gonna go here. All right, so here's an example. This is from a very cute paper by, not really a paper, it's like a, more of a pop piece by Marvin Minsky of a symbolic apple and a connection apple, which I think maybe might make things a lot clearer for you. So a symbolic apple, you can see in this tree structure, has different properties. So it comes from an apple tree. It's a member of fruit structure. It can separate into the body and the stem. So kind of the symbolic approach is really more like the relationships between things that kind of needs to be written in. The fact that you have categories like fruits that you can be a member of, for example. These are things that are put into the system. Whereas on the other hand, now this new approach is called connectionism, also called PDP, parallel distributed processing, but no one calls it that anymore. That's just if you see PDP in some old literature, whereas good old-fashioned AI is still often used. So in connectionism, cognition is thought to be more recognizing patterns or finding structure in the world. And it learns the structure through basically many examples and stores them in the weights. And so really the important components for symbolic AI are symbolic manipulation and for connectionism, it's more like learning and lots of data. Some of the problems with this are that it's hard to interpret. So here's the example of the connection apple. So you can imagine this is like a neural network that has been trained to respond apple every time it gets some input that is like visual input that is an apple. And so you just get like a bunch of numbers, and how do you interpret this? This is still a problem today, and one that there are people working on the interpretability of neural networks now. So that's active body of research. Another problem with it is that you need a lot of training data and computational power, which was a big problem back then. It's less of a problem now, but still maybe a problem. But both of these were inspired by McCulloch-Pitts. So first symbolic, because McCulloch-Pitts was really more of a symbolic type model, but then later connectionism as well. Any questions on the difference between connectionism and symbolic?
Yes, so with the symbolic AI approach, how is it proposed that we learn anything in the first place?
Sorry, in which approach?
With symbolic AI, if it's required that the structure is sort of hard-coded already into the network, how is it proposed that we can learn anything, like developmentally?
Yeah, it's a really good question. I think it is assumed that it is hardwired, but I'm not sure if there are some people who are thinking about how you could actually learn these types of, how you could actually learn these relationships. I'm not sure. Very good question.
Does it have to be, sorry, can you hear me?
Yep, yes.
Does it have to be completely one or the other? Could you have a kind of a mix of the two?
Nope, you can add, absolutely.
Grammar, for example, could be
yeah.
effective learning vocabulary.
Yes, you could absolutely have like a combination of the two. In fact, there are more recent calls to mix these two because cognition is likely to be some kind of combination of these two things, or maybe there are like faster processes that are more connectionist-like and slower processes that are more symbolic-like, for example. But this is, historically speaking, it was a big rift. But I think most, maybe most people now who are not like really strongly entrenched in one side or the other agree that like a combined approach could be better. Right, there's a comment. With symbolic AI, the problems seem to be inherent to the approach. They look like deeper problems than with connectionism, where they look more like implementation problems. Juliet, you must be a connectionist. Just a joke. So I think it's definitely very tempting to think that there are more problems built into symbolic AI, and that's definitely that's also, if I had to choose one or the other, I would go with that. But I think it's also important to keep in mind that there's been a big resurgence of connectionism, and there are a lot of problems with deep learning and with connectionism. Problems, it kind of depends on what you mean by problems. Problems in terms of describing how people learn, for example. One of the very classic ones is that deep networks are very powerful, but they require a huge amount of data in order to do any learning. And it's pretty clear that children don't need huge amounts of data in order to learn, at least in some particular examples. Like language, for example, is classic, like poverty of the stimulus arguments. You don't need to know every single possibility of different of words to learn. So I think it's pretty much widely recognized now that there's something wrong with, or not, wrong's the wrong word, incomplete maybe, with these connectionist style approaches, at least with deep learning, that it's missing something about how humans learn. And that's like that is an implementation, or sorry, that is like a deeper problem. It's not an implementation problem. And that'll come up later. So later in the course. The black box issue from Constantine is a major problem. I completely agree. Practical and ethical, I think, for the massive implementation of deep learning. It is a current research subject to explain how algorithms find answers. I had a long chat with an informatic researcher working on that subject this afternoon. It's very interesting. That is, I completely agree. Yeah, there's like every week or so there comes an example of some particular deep learning model that's like racist in some way or sexist or something. Like there are real problems with ethical real world problems with just trying to find structure in the data without having any kind of anything built in. Just like reflect the problematic assumptions of the world back at you. Does someone want to say something because they unmuted themselves? Was there a comment? No, okay. Yeah, and also the black box issue is also a real problem. I mean, if you're interested in how cognition works, then you're probably not going to be satisfied with like cognition works as like a gradient descent in like a high dimensional space, which is the argument of some researchers that I think that's in a couple lectures that you'll read about. By the way, I mean, feel free to reject any of my opinions. I really want you guys to be able to be critically thinking about this for yourself. So if you think I'm wrong, don't be afraid to say it. There is no learning in the sense of deep learning, but some logical rules can come from the simple ones that are encoded. Logical AI was used to automate some job. We asked two experts what they were doing when they pushed which button implementing the machine. Some rules emerge without being implemented. what exactly, so do you mean that it's just probably me, I'm just not understanding. Can you repeat that, or maybe with your mic?
Yeah. Can you hear me?
Yes.
Yeah, I learned that symbolic AI was used to, we asked experts what they were doing, like, as I said, when they pushed this button, when this light was on, I pushed this button, and it was like very oral and very like we had to ask people what they were doing, and we implemented these rules into machine to get rid of these people because the job was too dangerous or thing like that. And implementing this basic and this expert rules, some rules could appear, could emerge, but it's not, there is no learning from the machine, but they could be like link between rules that the expert didn't the expert could be not aware of the simplest rule or thing like that. I don't know if it's clear, but
sorry, are you saying that basically there's not real learning in the sense of learning some kind of structure or like model the world? It's just like developing weights that
yeah, it's just like logic. And because if the experts say that if I have A, I do B, and next he say another logical rule, the system can simplify this and make inferences, but there is no learning and no improvements from the part of the machine, I guess.
So this is about sorry,
no.
It's about expert systems, or
it was about the symbolic AI, which could learn or not. I think it was Betty question. I'm not sure. It's different. It's not machine learning. It's another part of AI, and AI and machine learning is there is like the AI and the machine learning is a part of it, but symbolic AI doesn't fit in machine learning.
Right, exactly. Less of a focus on the learning side. All right, so I'm actually, so this is great. I love the discussions. I should continue to get to the end, but then we can talk more. All right, but we're almost near the end anyway. Okay, so I just want to point out the famous XOR problem, which is if you have X1, XOR, meaning exclusive OR, X2. So here's the kind of logic, the logic square for that. So it's, you want your downstream neuron to be active if only X1 is active, but X2 is not active, or the opposite, if only X2 is active and X1 is not active. And so if you put this in the kind of the colors that I put before, in this other representation of this, of the input space, how can a perceptron solve this?
It counts?
Yes, it can't. Because there's no line that you could draw to separate these, the blue and the red dots. There's no line you could draw. You'd have to draw some kind of like curve that, you know, does that or something. So this is a classic problem with perceptrons. It's mathematically impossible to separate the blue and the red points with a line because the problem itself is not linearly separable. Can a McCulloch-Pitts network implement XOR? Yes or no? You can vote with your non-verbal feedback for yes or no on this. Okay, getting mostly yeses, a few nos. Hogue asks, single layer? No, I do not. I mean, a McCulloch-Pitts tile network. Multiple layers are allowed. So I guess I know what you're voting. Okay, so some yeses, some nos. So you can implement this. So you can write XOR logically as. Sorry, did someone say something? Who was that? Was there a question? Was that just a reaction? All right. X1, XOR X2, you can rewrite this as X1 or X2 and not X1 and X2 because it has to be exclusive OR. And then if you label these new propositions as Z1 and Z2, then Y, your downstream, would be Z1 and not Z2, which comes from, which gives you X1, XOR X2. Anyway, the actual logic doesn't matter that much, but just that you can actually reduce these into the logical operations that I showed you how to implement, and you can just put them together. These are just the three examples I gave you earlier of and not, or and you have a McCulloch-Pitts style network that is able to implement XOR. And so I had this question for you, but somebody already anticipated it. What's different about this network versus the perceptron is that the perceptron only has one layer, at least the classic perceptron, and the McCulloch-Pitts network doesn't have this type of limitation, so it has an extra layer. The reason the perceptron only had one layer is because basically somebody had mentioned backpropagation had not yet been developed at this time, so you couldn't do the learning for multiple layers. But it is true that if you have a multi-layer perceptron and you have backpropagation, then you can solve this problem. So it's, and basically adding an extra layer means that your multi-layer perceptron is able to solve non-linearly separable problems. I mean, this is a side point I can go into again in a later lecture. But the important thing is that the perceptron, by only having a single layer, is not able to solve this problem because it can only solve linearly separable problems. So this leads into the first AI winter. There are actually two, one in the 70s and a smaller one in the 90s, but let's talk about the one in the 70s first. So this was a massive drop in funding and an abandonment of connectionism that happened until sometime in the 80s. There were many different factors, but one of the factors was this book by Marvin Minsky, who I pointed out in the Dartmouth Summer School. So he, in papers in 1969, wrote a book called Perceptrons. So before then, nobody had really studied like the mathematical implications of perceptrons. So in this book, they showed the limitations mathematically using proofs of perceptrons, and one of them was this fact that they can't do non-linearly separable problems. And then I think there was actually like a reply by Rosenblatt or something. It's not that he didn't know this, and then showed that you could do this with a multi-layer perceptron, but the damage was already done by this time. And this is one of the factors that led to the reduction in interest of these types of models. There's also just general pessimism about the promises and the achievements of AI. The promises, I mean, if you remember this New York Times article about like an embryonic brain developed by the Navy that is going to learn how to think. It's kind of surprising that there was later pessimism about the state of consciousness in the perceptron. So in the UK, there was this Lighthole report in 1973 on the progress of AI, which basically trashed the field, saying it was by an applied mathematician named Lighthill. He was saying that all of the progress in AI had essentially been related to like very specific problems, but there's no progress in general AI.
Excuse me. By this time, had they already incorporated the activation functions into multi-level networks?
I don't know, but maybe not, because the actual algorithm that was used for the original perceptron is different from what we think of as like the gradient descent type algorithm that we would use today. But the bigger problem was not the activation function, but it was basically back propagation just wasn't developed.
Well, sure. I just mean to say another weakness if they hadn't had incorporated activation functions is that just like feeding forward weighted averages like this is equivalent as just a linear regression. It's equivalent to a linear regression.
Yeah.
Without activation functions.
I don't know if they had other activation functions or not. Is the short answer. I don't know. Okay. Let's see. Oh dear. I do want to show you a little bit of this video, but so I think the thing is, I'm afraid I'm going to take 10 minutes just to figure out how to. Sure, are you guys still there? Still alive?
Yeah.
Okay, this might be a disaster, but I might as well try it now on the first. Okay. I think this is the one I want to share. Can you see this? Actually, this is the class Moodle, so maybe I'll just show you around here while I'm here. Basically, you have the announcements that I'll use to tell you if anything urgent pops up. Link to the course syllabus. Here's you can discuss ideas. This is what Betsy was asking about. I wrote just something to give you an example. You can introduce yourself if you feel like it. But I'm hoping you guys will add more discussion topics that are more argumentative and debate-like, and then I can read them and respond to them. That'll be really fun. Oh, this is very experimental class, so you can also give general course feedback. So this is completely anonymous. So you can submit a complaint or a praise. Feel free to submit praises as well as complaints. And then this is the structure. So I'm basically gonna have like a folder that has here the reading and the quiz are online. Okay, so now the thing is, I want to show a little bit of this video, and I'm not sure if you'll be able to hear it. All right, can somebody say something?
Yeah.
Okay, so let's see. Let's see if this works. Tell me if I'll put the captions on just in case. All right.
I shall argue that these were eminently good and sufficient reasons for embarking on the work 20 or 10 years ago. In practice, however, the line of approach has led to somewhat disappointing results in these respects. We have acquired rather little generalized information applicable to a wide range of automation problems. Instead, we find that specialized problems are best treated by specialized methods, and I shall try to explain why that is. Similarly, the sciences of psychology and neurobiology have benefited not from robo work in general, but from those computer models that take into account really extensive bodies of experimental data on psychological behavior or on nerve cell networks in the brain. Before I expand on these reasons for a certain disenchantment with robot research, I shall predict that people nevertheless will go on building them. At all periods of history, the human imagination has been captivated by the idea that the mysterious arts, whether of the sorcerer's cell in earlier times or the scientist's laboratory today, might be used for a process of, as it were, artificially giving birth.
Okay, so I think you get the idea. So the reason, so this is this man here is Lighthill. So he is the mathematician who is giving out to a panel of enthusiasts of artificial intelligence. One of whom is McCarthy, who is one of the who was the guy who coined the term artificial intelligence. I do remember. Let me If that worked, right?
Yes, sorry, yeah, it works.
Okay. Thank you. Let me go back to the presentation. Okay, so I think there was, oh dear. Okay, so there is a problem that now my two, there's a reconfiguration. Sorry, so I just need to not mirror the displays so I can actually see what people are saying. Okay. Okay, can you still see my slides?
Yes.
Great. I'm having trouble finding where you guys are. It's the perils of mixing different applications in Zoom. Are you still there? Oh,
Yeah.
there it is. Okay, yeah, obviously it was my fault. Okay, let's pretend that didn't happen. Okay, great. No, this is fine. Okay, there was, because I saw there was some kind of question somewhere. But I've lost all of the windows. Can somebody read out the question because I can't find the chat?
I think there is no question.
Okay, great.
Okay.
Never mind then. Okay, so let's sorry. Okay, let's go back to the Lighthole report. So yeah, so the reason I'm showing you this, so this was based on the actual report that he wrote. This was like a popularly screened BBC debate debating the promises of general artificial intelligence. And the reason that I'm showing it to you is because it's your reading. So your reading is technically a video for this week. Okay, and of course, we know now that there's been a massive comeback from connectionism, both in terms of like object recognition in vision. So here's an example from AlexNet, very famous deep network that's able to classify different images with very high precision and very high confidence in some of these cases. And then, of course, there's the very famous recent example of AlphaGo, which was able to beat the leading champion at Go. So clearly, there's been kind of a reversal from before of connectionism becoming much more popular than symbolism recently. Although there also have been recent calls to combine both of these approaches to get kind of the best of both worlds. But what I would say is just taking into account the kind of history of how these ideas came around and the kind of switching back and forth from connectionism and symbolism, as well as the larger history of metaphors about how the brain works, going all the way back to ancient Greek society. I would just say, don't get too sure that any particular model that you're working on is definitely how the brain works. Okay, so that ends our class right on time, about 5 minutes over. Key things for next time. Okay, first of all, get on Moodle. I'm really sorry that there is a lot of difficulty with this. Is that a question?
There's a question on the chat.
Okay, let's see. Any examples of recent calls to combine GoFi and connectionism? Technically, AlphaGo is, some people consider this as a combination of GoFi and connectionism because it's like deep reinforcement learning and then it has some kind of like true search algorithm. So that would be one example. Any other questions? Okay. So yeah, to wrap up. So it's important that you get on Moodle because everything is going to be through Moodle, and it's a little bit of an experiment because I volunteered to try out Moodle, so that's why it switched from Schoology to Moodle because there's some consideration of moving things to Moodle in the future. Yeah, the most important thing is to get on Moodle. So quiz 1 is due next Tuesday at 5. Exceptionally, after then, it's going to be due on Wednesday. So that's really why you need to get to Moodle in order to submit the quiz on time. Otherwise, it's going to be counted as your one quiz grade that's dropped if you're not able to complete it, and then you get a 0. Reading 1 is the Lighthill report. Oh, sorry, it's not actually not the report itself. It's the Lighthill debate. So I guess because I think there's actually not that many people who are able to get onto Zoom, I will send an email. That email is going to include the Lighthill debate, and I'll write like the little blurb that I had put on Moodle for that. So I'll include the reading. I'll include a link to the YouTube video where I post the recording of this lecture. Is there anything else I need to send? I don't think so. And next week, I'll see you for neural excitability, what makes a neuron spike. And are there any final questions here?
Yes. I am not on.
Hello? Oh, where did that, hello? Okay, well, send me an email if you're still there. I'm not sure who that was or where that went. Elizabeth asks if I can send the slides, and yes, I will. Ines asks, when would the quiz be available? The quiz is available from 5 p.m. on Tuesday, so it's available now. So if you are on Moodle, you can take the quiz. If you're not, get on Moodle so you can take the quiz. And it's basically you get one try to do this online quiz, and you have 15 minutes to do it. It's only 10 questions. And so you just need to block out like a 15-minute period of your day within 24 hours, except for, this first week when you have a whole week.
Will there be any optional additional readings?
Do you want optional additional readings?
I don't know. It depends.
On how interesting
on the contents, yeah.
Yeah, I kind of like went back and forth on this. I mean, I could put some, different resources there if you're interested in learning more about them. Yeah, I could put them in the Moodle and then have a heading that says optional. Any other questions?
Are there penalty points on Moodle for the quiz or not?
What is a penalty point?
Well, like minus point, like if I choose the wrong answer, then I get a minus point, or like minus.
Oh yeah, there's only one, because I couldn't figure out how to do a question that was like check all that apply, and so there's like one where if you check the one that doesn't apply, and I'm already giving you a big hint by saying that one doesn't apply in one of the questions, then you get minus 100, so that you get 0, but you don't get minus points, but it basically invalidates the other points you would have gotten for the correct answers for that particular question. That's only one question though. I mean, I don't want to do like anything really complicated in general with the quizzes. Anything else? Let's see, great. Well, I actually had an exit poll, but now I can't find anything. So I might just make a, basically this is the first time this class is being offered, and it's very experimental to have this kind of a computational class that's not really mathematically based. So I would very much like your feedback on like every, I'm gonna try to make a form that you guys can fill out for every lecture. That's gonna be completely anonymous because I really want honest feedback on whether the content was too fast or too slow, on whether the math was too fast or too slow, and on, yeah, general, like you find, yeah, other kinds of things. So I will send that in addition with all of the other materials and would be grateful if you would give me your thoughts. All right, thank you, and see you guys next week.
Thank you.
Bye. Thank you. Bye.
Goodbye.